All right, let's dive straight into this explainer. If you're prepping for a quantum computing exam, you probably already have a handle on the basics. Qubits, superposition, the usual suspects. But right when it's time to actually test your knowledge, the Deutsch-Jozsa algorithm pops up as that first massive hurdle. It's the one that really tests if you understand how quantum mechanics actually computes. So today, we're going to break this whole thing down into the ultimate quick study guide. No getting bogged down in endless equations. We're going to visualize exactly what the math is doing under the hood. Here's our roadmap for today's session. We'll quickly run through the constant versus balance problem, compare classical versus quantum speed, look inside the oracle, demystify the Ket and phase kickback, walk through the math and interference, and finally, look at the final measurement. Okay, part 1, the constant versus balance problem. So, picture this. On your exam, you are handed a mystery black box, an oracle. You feed it a binary string, and it spits out either a 0 or a 1. Now, the absolutely crucial thing to grasp here is your two possible realities. You have a rock-solid guarantee that the function hidden inside this box is one of exactly two types. Option 1, it's a constant function, meaning no matter what you put in, it always spits out the exact same number, all zeros or all ones for every conceivable input. Option 2, it's a balanced function. That means it's perfectly split right down the middle, returning 0 for exactly half the inputs and 1 for the other half. Your one and only job is to figure out which of those two boxes you're holding. Moving right along to part 2, classical queries versus quantum speed.
To really get why this algorithm is a game changer, I want you to think about how many questions you have to ask this mystery box to guarantee, like absolutely 100% guarantee, that you know what's inside. Let's say you have a 3-bit input, right? That's 8 possible combinations. You query the box once, you get a 0. You query it again, another 0. Honestly, even if you query it 4 times and get 4 zeros, you still can't be entirely sure. It could be a constant function of all zeros, sure, or you might have just randomly stumbled on the 4 zeros of a balanced function.
For a classical computer, you have to look at the absolute worst-case scenario. You literally have to check half of all possible inputs plus one more just to be mathematically certain. To put that into perspective, if you're dealing with a 100-bit input, you would need over 633 quadrillion queries to be completely sure. 633 quadrillion. Classically, as the inputs scale up, solving this becomes literally impossible. And boom, this is exactly where quantum supremacy steps into the spotlight. Because the Deutsch-Jozsa algorithm solves this problem in exactly one single query, every single time. It literally does not matter if your input is 3 bits or 3 million bits, just one query. That's the quantum magic we need to unpack.
Which brings us to part 3. Let's look inside the oracle.
So to figure out how a single query actually pulls this off, we have to demystify what is physically happening inside that black box. You can't just run normal classical code on a quantum machine. You need a quantum oracle. And here's the catch. Quantum gates absolutely must be reversible. In a normal computer, an AND gate destroys information. If you just see a 0 at the end, you can't reverse engineer what the inputs were. Quantum mechanics strictly forbids destroying information like that. So we preserve the input, we'll call it X, and we bring in a target qubit, let's call it Y. Then we use an exclusive OR, an XOR operation, to securely write the function's answer onto that target qubit without losing any data. And you don't even need wild abstract math to visualize this. You can literally build this oracle using simple reversible gates. For your exam, just remember this rule of thumb. A constant function oracle is practically just an identity gate. It basically does nothing. It doesn't entangle or fundamentally change the state. But a balanced function oracle, that acts a lot like a series of CNOT gates, flipping the target based on the inputs. That reversible logic is the whole reason this operation is legally allowed in the quantum realm.
All right, part 4, the Ket and phase kickback.
Okay, we need to clear up the single biggest mathematical roadblock that trips up almost every student. When you're staring at your textbook and you see that Ket X notation inside a giant summation representing all the inputs in a superposition, remember this trick. X is just the binary label for the physical qubits. It is not a variable substitution like you'd see in classical algebra. When the math says sum over x of ket x, all it's doing is listing out the possible physical states. Ket 0, 0 plus ket 0, 1 plus ket 1, 0, you get the idea. X is literally just the name tag for whatever state those physical qubits are holding in that exact moment. Now for the main event. Setting your target qubit to the minus state triggers a phenomenon called phase kickback.
And guys, this is the absolute secret weapon of the entire algorithm. Because that target is sitting in a very specific minus superposition, when the oracle runs its XOR logic, the actual 0 or 1 bit value of the target qubit doesn't flip. No, instead, the mathematical result of the function gets kicked right back up into the input qubits.
So rather than changing a qubit from 0 to 1, the oracle encodes the function's answer purely as a positive or negative sign attached to the input. Think of it like a sticky note. If the function evaluates to 0, it sticks a positive 1 on that state. If the function is a 1, it slaps a negative sign on it. Boom! Suddenly your massive superposition of inputs is secretly carrying the answers to every single possible query, hidden entirely within those positive and negative phases.
Now, it's super important to clarify a common misconception here. Quantum speed isn't just some non-deterministic process where the computer magically guesses all paths at once and verifies the right one. A non-deterministic algorithm is just a theoretical computer science model. Quantum computers aren't magically guessing anything. They are physically, actively manipulating these positive and negative phases across all possibilities simultaneously.
Next up, Part 5, Math, Walkthrough, and Interference.
Let's synthesize all of this. If you can memorize these 4 simple steps, you have completely mastered the mechanical flow of the algorithm. Step 1. Start clean. Set your query qubits to 0 and your target ancilla to 1. Step 2. Apply Hadamard gates to everything. That creates your massive superposition and, crucially, pushes that target into the minus state. Step 3. Run the oracle. This triggers the phase kickback, coding the answers as positive and negative signs. And finally, Step 4. Apply Hadamard gates to the query qubits one last time. This 4th step, that's where the real magic happens.
Which brings us to our last section, the final measurement.
For the grand finale, you have to realize that second set of Hadamard gates wasn't just there to undo the first set. It forces all those phases to crash into each other, literally like ocean waves. If the hidden function was constant, all the phases match. They're either all positive or all negative. So when those waves crash, they amplify each other perfectly. That's constructive interference. The result? A 100% probability of measuring all zeros. But if the function was balanced, exactly half the phases are positive and half are negative. When the Hadamard gate shoves them together, they perfectly cancel out. Destructive interference. The probability of measuring all zeros drops strictly to 0%. It becomes physically impossible. So, you just measure the qubits. If you see all zeros, it's constant. If you see literally anything else, it's balanced. One query, complete certainty.
Now, sure, nobody actually needs to identify constant or balanced functions in their day-to-day life. But Deutsch-Jozsa was a brilliant proof of concept. It proved that by using superposition to probe all answers and phase kickback to create interference, we can take a problem that requires exponential classical time and absolutely crush it into a single quantum step. This exact framework is the DNA for almost every major quantum algorithm we use today. Which leaves us with a pretty wild thought. What other impossible computational bottlenecks is quantum mechanics going to shatter next? Keep that in mind as you prep for your exam. You're going to crush it.